talks about a correlation. And it's looking for some relationship between two quantitative variables, some x and some y. Like maybe there's a relationship between the number of pets you have and the amount of money in your wallet right now. I doubt it, but maybe there is a relationship. Or there's definitely a relationship in general on people's heights versus their shoe sizes. It tends on general that people who are taller have bigger feet. Not always true, but in general it's kind of a trend. So we're looking for that relationship. And the way we can visualize it is with a scatter plot. We made scatter plots back in August, it was a while ago. The 3 pictures I have at the top of the page here, those are all examples of scatter plots, where you plot the XY points like you learned back in algebra. So for example, the first one is about the size in carats, probably of diamonds, I would say, and the prices. So there's a little dot where you find the size, you find the price, put a dot there, and so forth. The other ones aren't really labeled, so we don't know what they're measuring. Remember scatter plots from before? We're going to create a couple today. So what we're looking for is looking to see which one of these, or if any of them, show a linear relationship, a line that kind of goes through the data points. Which of these looks most like a line? The first one for sure, right? You can practically draw the line right through there, see where it would go. How about the second one? The second one look like it has a line through it? A little bit, she says. Is that line going up or down?
Down.
Yeah, you can kind of put a line through there, starting from the top and kind of going down towards the right-hand corner. It's not a real strong line. I mean, it's not like they're definitely lined up, but you can at least see where the trend would be. And what about that last one? No, I mean, which way would you draw the line? I don't even know where to guess either. So we talk about the first one being a strong correlation, the middle one being a weak correlation, and the last one having no correlation. So how close it is to a line is how much correlation it has, how strong it is. And we use the letter R, which is right underneath those pictures, to be the linear correlation coefficient. And there's a little description of R in the middle of the page there. R is always a number between -1 and 1. It can't go past those. If R is 1, then your data points are in a perfectly straight line that goes up. So kind of like that first one, if they were perfectly straight, R would be exactly 1. And if the second one was perfectly straight, which definitely it's not, going down, then it would be -1. So the sign just tells you if it goes up or down. And how close it is to 1 is how close it is to a perfect line. And guess what 0 is? No correlation, which would be probably what we have on that last picture, right? There's no correlation, so R will be really close to 0, if not 0 in that case. So what I want to do is just estimating with those 3 pictures. I'm going to call them A, B, and C. The 3 pictures. What kind of number might you assign, if you had to guess, what kind of R would you put with any one of these? There could be 3 different R's. We just talked about this one. The third one? Third one would be 0. There's no correlation that we can see there. How about the first one?
1.
Is it exactly a perfect straight line?
No.
So it can't be exactly 1. So
0.9.
she's close. 0.9, is that what you said?
Yeah.
Yeah, so something close to 1, but not exactly 1. I like 0.9. It's kind of like probabilities, right? Where the closer you are to 1, the closer it is to be guaranteed. You can't tell by looking what the number actually is. So if you had said, I think it's 0.8, I wouldn't have argued with you. But it's closer to a straight line than not. So it's something, closer to 1 than 0. What do you think you might put for B?
0.5?
0.5?
Negative.
Negative 0.5. She's corrected that. You see why it has to be negative? Negative because it's going down. It might be slightly lower or higher than 0.5. We can't tell by looking. But the thing you're looking for is the closer the number is to 1, the closer it is to a perfect straight line. And the farther from 1, the more likely is there's no line there at all. You okay on what we're looking for there? Okay, so let's start the first example by drawing a scatter plot. So example 1A asks us to construct that scatter plot. 1A. And they give us all of these XY pairs. They don't really tell us what they represent. And they want us to put them on our graph. I give you a piece of graph paper on your notes. What should I count by for my x's? What do my x values go from? Maybe count by ones, because we have to go up as high as, what's the highest x? 14 is the highest x, so maybe we count by twos. You guys could probably count by ones on yours, but I can't quite fit that up here. So maybe I'll count by twos. 2, 4. You could probably count by ones on your graph paper I gave you. We just want to make sure we fit all of the x values that go up to 14. If they went up to 140, maybe I would have counted by 20s or something. And then what about the y values? They go from, I see a 3 up to 9 point something. So maybe I'll just count by ones for my y values. You guys might be able to go every other one on yours, I don't know. This might be going a little bit too big, we'll see. I have to extend it up a little bit. So the first thing you want to do is mark your axes to fit your x's and your y's. Now it's just algebra review, right? You think of these as pairs. The first one, 10 goes with 9.14. The first pair there. So I'm going to come over here to 10. I'm going to go up to 9.14, which is approximately here. And put a little dot there. 9.14 is a little bit above 9. See what I'm doing there? Remember this from your algebra days? And the next one is 8 and 8.14, so I come over here to 8. I go up a little bit past the 8, which is roughly here. So do me a favor and take a minute and try to put the rest of those in there. See if we get the right picture. Did you get something like this? Mine's kind of smushed together because I don't have my graph paper there. Yours is probably better, but look something like that. So that's the example of a scatter plot. We did scatter plots, like I said, back in August, which feels like forever ago. So now if I handed you this one along with those other ones we did earlier at the top of the page, and I asked you to estimate R, first off, do you think R is positive or negative?
Positive.
Positive, why?
The majority of it's going up.
Yeah, most of it's going up in general. If you kind of stepped way back, you'd see this trend going up. So I agree that it's positive. Some positive number. This is our estimate. Estimate has a T before the I. There we go. What kind of number do you want to use? It's just a guess. I don't care if we're wrong. I just want an educated guess. 0.95? Why do you say 0.95?
Oh, it looks like a really straight line, almost a straight line. But there is a curve, so.
So yeah, she said it looks like almost a straight line and then it kind of curves down. So what does that little extra curve do? So she wants to go as high as 0.95.
I was gonna say 7.5.
You want to say 0.75? And why do you say 0.75?
This goes up and back down.
Yeah, because it does go up and then it goes back down. So I can agree with that too. We're actually going to be able to calculate it in a minute here to see what it actually is. Anybody have a different guess? You say 0.80, it's a little bit higher than that. These are all guesses. Notice that they're all positive because it's going up in general. And they're all more than like 0.5 because it's pretty close to a line. And so there's this whole very nice, messy, long formula on how to calculate the R, the correlation coefficient, but instead we're going to ask our calculators to do it. So over there on the right, at the bottom of page 144, down here, are the directions on how to get the R coefficient. The first thing we're going to have to do is the same thing we've been doing all semester, is to put the two lists into our list 1 and list 2, or any two lists that you want.
I think 73.
Did you already do it?
No.
Something tells me that he's psychic. I'll put this down for a second. So type all your numbers into your list 1 and list 2. Okay, you got them all typed in there?
Yep.
And then, if you look at the directions, it says to go into stats and tests. So the same thing we've been doing with all our other tests. So I'm going to go over here to stats. Come over here to tests. And it's called a linear regression t-test. We're looking for this linear regression. It's called a linear regression t-test. Short is LINREG. So I'm going to go down, pretty far down there. Computer's on delay here.
Oh, I think I missed the number.
Did you miss the number? So it's not 0.73? You're not psychic?
It might not be. Well, it says my degrees of freedom are 9. I think there's 11 problems.
Ah.
1, 2, 3,
Linear regression t-test?
7, 8, 9, 10, 11.
You guys probably found it faster than I did.
Yeah.
You're fixing yours now, Brian?
Yeah.
Okay, so when I hit enter, it wants to know where I put my data. So we put ours, I put mine in list 1 and list 2, but if you put them somewhere else. The frequency is always 1, like it has been for all of our other tests. We're going to always choose the not equal to. We'll get to that in a minute on why that is.
Mine says 9.
And then we're going to come down here to calculate and hit enter. Just leave the REQ as blank. And you get something that looks like this. Tell me if your numbers don't match mine, so it means I typed something in wrong. Do we agree? Disagree? I got Liam nodding. Most people are nodding. So here's the bad news. If you didn't get my numbers, it seems like you made a mistake. Because other people agreeing with mine. What were we looking for? R. I don't see an R there. Yeah, see the little arrow? Tells me to keep going down. So keep going down and find the R. So I'm going to go down with my arrows. Oh look, there's R. I think Evelyn wins. 0.816. Right up here. R equals 0.816. So the first couple homework problems in this section will be create a scatter plot and find the linear correlation coefficient. That's the beginning part there. Questions on how I did that? So then the question is, how high, so this is our actual R value. What's the actual R value? So this guess is a little bit too high, a little too low, so pretty darn close. You can't just tell by looking. But the idea is, well, how high is high enough to say there really is a pretty good linear relationship? Right, because close to 1, what's the definition of close to 1, right? So it's the same thing like all of the other hypothesis tests we've been doing. What's that cutoff to say, yep, that's big enough to say there's a linear relationship? A linear correlation, we call it. So again, we have two ways of doing it. We've got critical value methods and p-value methods to decide if there's a linear relationship or not. So we actually will write out an entire test to go with it, a hypothesis test. You know how we used R for the linear correlation coefficient? That's for our sample that we just had. If you want to use the corresponding Greek letter that goes for the population, it's a Greek rho. You spell it R-H-O, rho. And you're not going to like the way it looks, so I'm horrible at drawing them. It kind of looks like a P, like kind of like that. It's a rho. Do I have an example of one on here? I don't. Bummer. I should have had one printed on here. I don't have one in our notes. You look at in our section of the book, or let's see if it's on here. It might be. I want you to see what it looks like because I can't draw them very well. No, it's not here either. Bummer. I should have an example of one for you, but you'll see it when you pull it up online. It kind of looks like P. It's actually an R. The Greeks are very different from us. Okay, so this is the linear correlation coefficient. It's important though that you not write it like a P. Like don't write it like this, because then I'll think you're talking about proportions, right? It's not a P. It looks like a P. It's kind of a script P in a way. It's actually a rho. It kind of has a weird little loop. this is the coefficient for the population. And this one was just from our sample. Similar to how we had an X bar and a mu, or an S and a sigma. Is okay what I'm talking about there? So the claim is always going to be testing whether there's a correlation or not. If there's not a correlation, what will rho equal? If there's not a correlation, zero. That's what it means to not have a correlation. And since it's equal to 0, that's always going to be your H0. This means there's no correlation. Rho equals 0 means there's no correlation, just like R equals 0. This needs to be underlined. I don't want to do that. So guess what H1 is? The equals within H0. Does not equal. Which is why I had you choose that option when we did the test a minute ago. And that means there is a correlation. So either there's a correlation or there's not a correlation. Only options we have here. You technically could have a problem that says test for a positive correlation, in which case positive would be greater than 0. But almost all the time, I can think of very few exceptions, you're just asked test to see if there's a correlation or not. So it's not even clear which one's the claim. Is the claim that there's no correlation? Is the claim that there is a correlation? We're just testing to see, is there no correlation or some correlation? So that's always, every problem here, going to be your H0 and your H1. Okay. And then we have our test statistic is our R. So this is, step 1 of our 5-step hypothesis testing that we do. Step 2 is get your test statistic. It's your R. So our R equals 0.816. That's our test statistic. What's step 3 of our 5-step process? Anybody remember? Ooh, that's step 4. Either get the p-value or the critical value.
So I'm going to cut out part of the video here because the video was talking about how to test whether to reject the null hypothesis or not using the traditional method. Of course, we use the p-value method. So in this case, we got a p-value of 0.002. That is less than our significance level, which was 0.01. So that means we're going to go ahead and reject the null hypothesis on this problem. You can always use the p-value method like we have done the entire class.
And the conclusion is tricky because you're like, there wasn't test the claim. It doesn't say test the claim that. A lot of you say, I'm just going to restate it. Now this one does say test that there is a linear correlation. So I guess we could say that this one is a claim. Because this one actually said it. You'll see ones coming up where they don't tell you what the claim is, and we'll talk about how to write the conclusion. So what's my conclusion?
There is sufficient evidence to support the claim.
There's sufficient evidence to support the claim of a linear correlation. So usually what we just write, though, is there's sufficient evidence to show a linear correlation. Questions on that part? So at the top of the page now, our notes will call it, I'm going to put a note right here, that now we're doing 10.2, page 148. Has this y hat equals b0 plus b1x? Looks like this. Some of you remember from your algebra life? Y equals mx plus b. You had to graph an equation of a line back in algebra. That's what this is representing. This is like your mx plus b. They have it out of order. Yeah, the slope and the y-intercept. We're actually going to use that in a minute to graph it. But it's finding the equation of the line. This is the notation our book uses to find the equation of a line. This is just what we used in algebra. Our calculator uses yet something even more different. But go back up to that screen. Actually, I should probably pull it back up here. The screen that had the results at the top of the page. I want to point to it while I talk about it to make sure we're clear. So after you do the linear regression t-test, before we scroll down, wait for it to warm up again. You see what it says at the very top of the screen there? Computer totally froze. Well, good thing it's still here. I can point to it. Can't move my mouse. Y equals a plus bx. See on the top of your screen there? That's the same thing that our book calls b0 plus b1x. So if you're doing an online problem and it says find the regression line b0 plus b1x, the b0 and b1 don't show up on our calculator, but our calculator shows us that it's a plus bx. And then look a little bit further down here. There's a and there's b. See how they're right there? They tell you which order to put them in, and they tell you which one's a and which one's b. Good? Yes?
That's like the supplemental, like the calculator's formula, but it means the same thing as that one?
Yes.
Y hat?
Right, I'm going to write my y hat down here in a second, as soon as I'm done pointing at this. But yeah, so the notation changes based on your book versus your calculator, but the same thing. You will be asked to find the equation of the regression line. And so this tells me to plug 3 in right here and plug 0.5 in right there. A is, it's part of the line. It's called the y-intercept when we go to graph it. We'll do that in a second. A and B are just the two numbers that go in the line. I'm about to put that in there and show you what to do with it. Everyone clear where I'm looking at A and B on here though? Turn it back off one more time. My computer decides to unfreeze it too. Doesn't want to go all the way up. Technology. So you guys all have those numbers in front of you. So our calculator calls it y equals a plus bx. This is the calculator notation. This is our book's notation and our notes. But no matter what, the directions are find the equation of the regression line. So based on the a and the b that we just saw there, our equation is y equals 3 plus 0.5x. Because a was 3 and b was 0.5. This right here is the regression line. Now here's an algebra review question for you. How do I graph that?
3 is the y,
3 is the y-intercept.
and then there's a 0.5 is, how many,
Remembers part of it.
you
3
go
is the
up and
y-intercept.
over, so.
Uh-huh.
oh, I know.
Good, she totally remembers it. So Evelyn mentioned before, this is the slope. The slope is 0.5, so you go up 0.5 and over how far?
Wait, no.
3. Up 3
No,
over
that's-
5.
3 goes
The
up,
slope is 0.5. That's your slope.
over
So-
1,
So you could write this as 0.5 over 1,
yeah.
or you could think of it as a fraction. 0.5 is 1/2, up 1 over 2. Jogging your algebra memories here. I'll show you how to get you the same thing either way. So from 3, I could go up 1/2
And then,
and over 1, which would put me about right here. Oops, I switched colors on you, sorry. I could go up 1/2 and over 1. Or I could go up 1 and over 2. See how it doesn't matter, I'll get the same line when I connect the dots. And then if I carefully and accurately connect these dots with a straight line, it looks something like that. Not very dark. Can you see that, Nick? Let me make it darker. Pretend it's a straight line. So that's the line that best fits our data. So we said, is it linear? Is there a linear relationship or not? Remember we said there is evidence of a linear correlation. So then the follow-up is, well, if there is, what's the line that best fits it? So this is the line that best fits it. So when the directions said on page 148 off to the side, it said find the regression line and graph it on the same axes. We found the line and we just graphed it on the same axes. So we're okay on finding the line, which is handed to you really, and graphing it. Graphing might take some review if you don't remember your algebra. Now the bottom of the page, there's very deliberate caps and bolds down there at the bottom of page 148. If there's a linear correlation between the two variables, if there was a correlation like we found in this case, that's a really big if. If there's a correlation, we can use this line to predict y values. We can use the line to predict y values. So if I come along and say, oh, I have a number that's 8.5, what's the y going to be? We can say, oh, it's going to be whatever it would be right here on this line. We're going to assume that line's the best prediction. We're about to make a prediction in a minute. But then the next line down, if there's no correlation, like my example earlier about how many pets you have and how much money's in your wallet, I'm not going to ask you how many pets you have and plug it into an equation to estimate how much money's in your wallet, because there's no relationship there. Where if you tell me how many hours you work, I can plug it into an equation and figure out how much to pay you, because there is a relationship there. So you don't always use that equation. You can only use the equation when you do have a correlation. If there's no correlation, then the best prediction is the mean value of y. So if you said, hey Jill, guess how much money's in my wallet right now? I'd say, hang on a second, let me see what everybody has, and then I'll just take the average of those, and that'll be my best guess. I'm not going to say, first tell me how many pets you have, because there is no relationship there. We'll go back to this, but that stuff on the bottom of page 148 is crucial, because every problem in section 10.2 asks you to get this line, but you can't always use it. You can't use it unless you have a correlation. We'll see an example coming up where there is no correlation. Questions? Example 1b. What's the best estimate for a y value corresponding to an x value of 13.5? So if I'm over here at 13.5 on my x's, we want to guess what this y value is up here on the line. How would I find it?
Just plug in 13.5.
Plug in 13.5 for x into my equation and figure out what y is. That's what this is doing. This is my line that makes the best prediction. So for 1b, my y hat, I didn't put my little hat on it. It's a hat. Doesn't really matter. I don't care if you write the hat or not, but the computer will. We're going to plug in 13.5 right here for the x. And we will get, let you guys do that,
6.75.
plus that 3, right?
Oh, 9.75.
9.75? Does that seem reasonable? If I'm at 13.5, does that look to be about 9.75? Looks like it is pretty much from my scale here. So this is my best prediction. We do not always plug the x's into the equation to get the prediction. We only plug them in when we find that there is a linear correlation, because then the line is our best prediction. If there's no linear relationship, even if your calculator can find one, it's a bad one, so we're not going to use it. Another warning is that this line only works for numbers between 0 and 14. If I came along now and says, hey, what if x was 30? I could plug 30 in here and get a number. I agree, it would work. But we don't know what this data does after this. What if it keeps going down? Then that'd be a really bad example for 30. So you don't ever want to make predictions outside of your interval because you don't really have any information about that. There's a couple in the lab who say, what's wrong with this? And usually because you're outside the interval.
So you only do predictions when there is a linear correlation.
See that again? We're
You
not
only do
talking to
predictions
me.
when there is a linear correlation.
Yes, you only use well, you make predictions, but you only use the line to make predictions when there's a linear correlation. Our next example will be what to do if there's not a correlation.